In this video, we are going to review determinants. In this section, we discuss the determinant function. Intuitively, the determinant function is a volume function. It assigns to a matrix the volume of the parallelopipe determined by the columns. You may also know the determinant is a function that determines if the set of vectors is linearly independent. In MATA 22, we learned that the determinant is a multilinear alternating function such that the determinant of I is 1. You may have also been introduced to the cofactor expansion definition of the determinant function. We begin this section by introducing an alternative but theoretically significant definition of determinant involving using permutations. Conclude this brief section by discussing some properties of determinants. You'll be expected to know the properties of these determinants and how to compute a determinant. I will not be asking you to compute a determinant using this permutation definition, but I do expect you know how to compute a determinant. Okay? Now, in order to understand a permutation definition, we need to know what a permutation is. A permutation, sigma, on a set 1 through n, is a bijection, sigma, which maps 1 up to n to 1 up to n. So it's mapping the set of numbers 1 to n to itself. Okay. Now, we let Sn denote all the sets of permutations. Now, when we say it maps the set 1 to n to 1 to n, what this means is that 1 doesn't have to map to 1. 1 could map to 5, it could map to 12. It maps to another number in the set 1 to n. But all the numbers from 1 to n get mapped to 1 to n, and it's bijective, meaning it's injective, surjective. Every number maps to a unique other number, and every number gets mapped to. Intuitively, we can think of a permutation as a reordering of the numbers. Given a tuple 1 to n, a permutation acts on the tuple, giving a new tuple or a new ordering. Okay. We can reconstruct the new tuple from the original tuple by sequentially swapping elements. The operation of swapping two elements is called a transposition. Okay. We might also know it as a pairwise entry swap. Okay. By swapping two elements, we are able to create any permutation. Okay. So let the permutation sigma be a permutation of 1, 2, 3, such that sigma of 1 equals 3, sigma of 2 equals 1, and sigma of 3 equals 2. Construct sigma by applying a sequence of transpositions. So we're going to start with the set 1, 2, 3, and it's an ordered set. And what we're going to do is I want to get 3 in the right spot. So I'm going to swap 1 and 3 to give me the set 3, 2, 1. And now I want to put 1 in the right spot. So I'm going to swap 1, or the second and third entry, to give me 3, 1, 2. And what you'll notice is here I said that second and third entry, but for simplicity's sake right now, we'll say let's swap the entries 1 and 2. Okay? So these are talking about the entries, but later we'll learn that when we talk about a swapping or a transposition, we're going to reference the locations for the transposition, not what's in the actual entry. Because remember, we could permute sets that aren't 1, 2, 3. They could be apple, orange, banana of some kind. Okay. If we're defining a set using a transposition, we can use the notation ij to denote the operation that swaps I and j. To apply multiple transpositions, we use composition. For example, KLIJ swaps the ith and jth entries. Then it swaps the kth and lth entries. When no swapping is required, we say that sigma is the identity. So there's a couple of interesting things about permutations or finite permutations. Every permutation on a finite tuple can be defined using a sequence of transpositions. So when we have this permutation, we don't need to know if it's a finite tuple, whatever that permutation is, we can define it using transposition. And the second interesting thing is that parity for the number of transposition required to define the permutation is the same, no matter how you define it. What this means is that you will either have to apply an odd number of transpositions to define the permutation, or an even number. And it turns out that when computing the determinant, this oddness or evenness for the number of permutations is super useful. But we'll get to that. First, because of this even and oddness in terms of the parity for the number of transposition, we can define the sign of a permutation, sigma. The sign of sigma equals -1 to the r, where r is the number of pair swaps or transpositions required. What this means is that if I have an even number of pair swaps, my sign's going to be 1. And if I have an odd number of pair swaps, my sign's going to be -1. So here, define the permutation sigma, which maps 1, 2, 3 to 2, 3, 1 using transposition, and determine the sign of that permutation. Now here we can do whatever we want, but what we're going to do is we're just going to take it one step at a time. And what I like to do is I like to move one element into the right space as we go. To one element, then the next element, then the next element. So I know that 2 is going to be in the first. I want to move 2 to the first, which means I want to swap the first and second entry. And this gives me 2, 1, 3. Now I want to put 3 in the right spot. So I'm going to swap the second and third entry to move that 3 into the right spot. This gives me 2, 3, 1 as 2 permutations were required. Sign of sigma equals -1 to the 2, which equals 1. Now what we can do is we can list all the permutations on S1. So what this is it's looking at all the ways in which S2 can permute the set 1, 2. We're going to list all the permutations on S2. To do this, we start with the set 1, 2, and we look at where it permutes it to. And what we're going to do is we're just going to list out all the different ways we could reorder the set. So the first way is just keep the same ordering, which we typically call sigma naught. And the second way is going to be to give us the set 2, 1. Now, what this means is sigma naught is the identity, and sigma 1, if we represent using transpositions, would be swapping the first and second entry. Okay, well, thus, my set S2 equals sigma naught sigma 1. And now, we're just going to, for clarity's sake, define what sigma naught does to individual elements. So sigma naught of 0 would equal 0. Sigma naught of 1 would equal 1. Sigma 1 of 0 would equal 1, and sigma 1 of 1 would equal 0. And this definition, sigma 1 of 0 or sigma 1 of 1, will be used within our definition of the determinant. Before we do that, we're going to kind of go a little bit overboard, and we're going to define all permutations of S4. So we have the set 1, 2, 3, 4, and it's going to be mapped using sigma naught to 1, 2, 3, 4. Okay. Now, what I'm first going to do is I'm going to list out all the possible ways we can permute these numbers, but in a very specific ordering. What I'm going to do is I'm going to keep the first few entries the same as long as I can, and then swap the back entries in a very specific way. So 1, 2, 3, 4. Because I have 1, 2, 3, 4, I have to swap this 3 and 4 to give me 1, 2, 4, 3. Okay, so now I have 1, 2, 3, 4. I have 1, 2, 4, 3. There's no other ways to write 1, 2 number. So what I'm going to do now is I'm going to bring the 3 forward. So 1, 2, 3, 4. This is sigma 1. Sigma 2 gets mapped to 1, 3, 2, 4. It's the lowest ordering I can do. Then 1, 2, 3, 4 maps in sigma 3. This is going to give us 1, 3, and now I'm going to do 4, 2. Okay. And what you'll notice is the value here is always going to go up. It's always going to increase. And what I can do is if I do it in this way, that it's the next highest, smallest number I can write, the next smallest number I can write, the next smallest number I can write. When I get to the largest number I can possibly write, I know I've had all the numbers. I started with the smallest number I can write. I end with the largest number I can write. I know I've got all possible numbers. 1, 2, 3, 4, sigma 4. Here I've done 1, 2. Now I've done 1, 3. Next I do 1, 4, 2, 3. It's the lowest number I can do, starting with 1, 4. 1, 2, 3, 4. Sigma 5 gives me 1, 1, 4, 3, 2. 1, 2, 3, 4. Sigma 6. If I look at it, this is the smallest number or largest number I can write with a 1 in front. So my next smallest number is going to have a 2 in front. 2, 1, 3, 4. 1, 2, 3, 4. Sigma 7. 2, 1, 4, 3. 1, 2, 3, 4. Sigma 8 is going to be 2, 3, 1, 4. 1, 2, 3, 4. Well, our ninth permutation is going to be 2, 3, 4, 1. Or I guess this is our 10th because we started at 0. 1, 2, 3, 4. Gets mapped to sigma 10. 2. This is the largest number I can do with 3, so the next was 4, 1, 3. 1, 2, 3, 4. Sigma 11 is going to be 2, 4, 3, 1. At any point, you can skip forward to the end of this part of the video. I'm just going to go and finish writing out all the possible permutations. 1, 2, 3, 4. 3, 1, 2, 4. 1, 2, 3, 4. 3, 1, 4, 2. 1, 2, 3, 4. Sigma 14, giving me 3, 2, 1, 4. 1, 2, 3, 4. Sigma 14, 3, 2, 4. 1. That was 14. This was 14. This was 15. 1, 2, 3, 4. 16. 3, 4, 2. 1, 2, 3, 4. Sigma 17. 3, 4, 2, 1. This is the largest number I can write with 3, so now I go into leading up with 4. 1, 2, 3, 4. Sigma 18. 4, 1, 2, 3, because this is the lowest number I can write with a 4 at the beginning. 1, 2, 3, 4. Sigma 19. 4, 1, 3, 2. 2, 3, 4. Sigma 20. 4, 2, 1, 3. 1, 2, 3, 4. Sigma 21. 4, 2, 3, 1. 1, 2, 3, 4. Sigma 22. 4, 3, 1, 2. 1, 2, 3, 4. Sigma 23. 4, 3, 2, 1. And here, what we've done is we've ordered them in such a way that the permutation output is smallest at the beginning to largest at the output. This is the largest number I can make using the 4 numbers. This is the smallest number I can make using the 4 numbers. This type of ordering is called a lexicographical ordering to list all possible entries. And the reason why we use a lexicographical ordering is because there's no question on whether or not we've included all the entries. We've gone from the lowest, we always write the next biggest the whole way up, and we finish with the last one. We know we haven't missed one. We know we have all possible permutations. Okay, now we go through and we need to determine the sign. Now to do this, we need to express the permutation as a set of swaps. So the first one is the identity, so the sign of sigma 1 or sigma 0 equals 1. The second one, we're swapping the third and fourth entry, so the sign of sigma 1 is -1. The third, or the second option, what we do is we swap the second and third entry. So the sign of sigma 2 is again -1. And the third, assigned to sigma 3, this actually equals more than just swapping 2 elements. We look at it and we go 3 goes to 2. So I'm going to swap 2 and 3. So I'm swapping those entries. And then after I've done this, I'm going to swap the third and fourth entries. This means that the sign of sigma 3 equals 1. Now I'm going to leave the rest of this as an exercise for you to compute out, but you can look at this permutations and you can determine what the sign is the whole way down. Turns out that with these permutations, we can define an expression for the determinant. The determinant of a matrix A is defined by the equation determinant of A equals the sum of sigma in Sn. So we're going to go through each sigma in Sn, and we're going to take the sign of the permutation, and then we're going to take A, and we're going to index 1, and we're going to use the sign of 1 for the first entry, sigma 2 times the permutation applied to 2 for the second entry, or sorry, A2, sigma 2, and then we're going to keep doing this to get to an sigma n. Another way to look at this is it's the determinant of the sum of sigma in Sn, the sign of sigma times the product of I going from 1 to n of AI sigma I. Now this might look like a more ugly definition of the determinant, but turns out theoretically this is a very powerful definition of the determinant.